Hi, I'm Ed Sperling. I'm the Editor-in-Chief of Semiconductor Engineering. I'm over at Brewer Science with Dan Sullivan, who's going to talk today about challenges of planarization at the most advanced nodes. Dan, what kind of problems are you seeing out in the market today?
Well, in the market today, as geometries get smaller, we need to planarize better. We're talking about getting down to less than a few nanometers of bias across globally across a wafer when we coat a film.
And so what does that look like in terms of you're building a chip at 7 nanometers, for example? What are you trying to do here?
Well, we're trying to coat, and typically what it is a gap filling material, spin-on carbon, we call it. We're trying to planarize the wafer for etch and for optical control.
Why don't you draw this out for us?
Sure.
What are we looking at here?
Okay, so I drew out a couple scenarios here. Looking at the old days of lithography, we could planarize with a pretty darn thick film. Had big features, we wanted to do etch, we had good etch transfer, no problems. But as things become smaller and more complex, with smaller types of features, you need a thinner film to planarize for etch control, but yet with a smaller film, it's more difficult to planarize. So it becomes a big challenge.
Why does the film have to be thinner?
Well, it has to be thinner because you have to build etch through in most cases. It's got to provide a reflectivity control, but it also has to get out of the way when you want to transfer images.
Why don't you break this down for us a little bit better?
Okay, so if you want to look at a big picture view of what's going on across the wafer, you're going to have dense features, some large maybe mesas, and then maybe large open areas. And ideally what you want to do is what this blue line represents is a perfectly flat film. But that's ideal. That's not what actually happens in a real case. What happens more like in this red line where you've got humps and bumps to fill across the features, and that's really not what you want.
In the past, when you were working at older nodes, was it actually any different, or did it just not matter as much because the films were thicker?
Yeah, it still mattered and it still happened, but you're right. When films are thicker, you had more etch budget, you had bigger resist or thicker resist features to work with. So yeah, it was much easier back then.
So what are some of the challenges you really have to deal with here?
Well, when geometries get small, you've got to be able to fill small features without any gaps. But also you got to worry about the substrate itself now, because we're talking about going from, in the past, maybe 300-400 nanometers down to 100 nanometers or thinner. You're really looking at how the material behaves on the surface itself. So the chemistry of the material here dictates how the material flows. A tinitride will work different than a silicon dioxide, as an example.
So if you're spreading film over a piece of cardboard versus a piece of glass, it's going to spread differently, right?
Yes. Materials will move differently, and if you had a difference in this area versus this area, they're going to behave differently and give you some weird effects sometimes.
What sort of material challenges are we looking at for upcoming nodes, 7 nanometers and beyond?
Well, we're really looking at processes going to higher and higher temperatures. So materials got to be able to withstand 350 to maybe 500 degrees C for maybe some extended period of times.
And do you always know where those materials are going to be used?
We don't always know where they're going to use. We expect in a lot of cases these are CVD applications where the material has to be able to withstand high temperatures in the CVD process.
We're going deep into material science here. What sort of chemistry challenges are you running into?
Yeah. To make a material that can behave or can withstand these temperatures for a long period of time, you really look at a small subset of the chemistries available in the world. You're talking about polymers that aren't very soluble in a lot of cases, and they also don't want to flow. So to get a material to go into a small hole can be very, very challenging. And also, when they don't want to flow, they also don't want to planarize. So you have to look at some really special chemistries to make that happen.
Does that make it impossible to move to future nodes, or are we just going to have to do things differently?
It doesn't make it impossible to go future nodes. There's still room for chemistry to be improved, but it may require improved processes, maybe CMP of carbon materials, or we've looked at developing back materials in the past, or maybe even go back to etch back type processes. But those all add costs to the process, so we try to minimize that as much as possible.
This is something that most of the industry really doesn't look at. How long has this been a problem, and is it just getting worse, or is there suddenly something that's changed?
planarization has always been a challenge, but I would say in the last 4 or 5 years, it's been really difficult to meet the needs of the industry, especially when it comes to these high temperature materials.
What's the impact of EUV on EUV?
And, if you want to talk about EUV, it comes back to this optical control. You don't really have that, right?
Yeah, okay.
So that's a helpful thing, but you're still talking about really small features etching. I mean, you ask how does it affect EUV? Yeah, there's other things too. Is that with EUV, magic happens. You don't know why things print better a lot of times. It's the chemistry way or underneath the EUV resist has impact on how the EUV resist work. Because honestly, we're going to be pushing our hard masks down to nanometers now, 10 nanometers thick, with a resist that's maybe 30 nanometers thick. So it's got an etch transfer. So then all your other stuff has to have the etch budget, and has to be small enough or thin enough to be able to transfer that.
What do you see as the impact of this as we get into the most advanced nodes?
I think the impact comes down to yield. If you can't control your process and the thicknesses don't work out, then transferring and optical control won't be there, and you'll get lower yields.
Dan Sullivan, thanks for a great explanation of a really interesting subject.
Thanks, Ed. Appreciate it.